Our story begins with a vast cloud of gas and dust, a cosmic nursery known as a solar nebula. These nebulae are scattered throughout the universe, remnants of past stars and the building blocks of future ones. Imagine a swirling mass of hydrogen, helium, and heavier elements, a chaotic dance of particles set against the backdrop of our galaxy. Gravity, the master sculptor, plays a crucial role here. As the nebula collapses under its own gravity, it begins to spin, much like a figure skater pulling their arms inwards. This spinning motion isn't just for show. As the nebula spins faster and faster, it flattens out, like a ball of dough being spun by a pizza chef. This flattening is a key step in the formation of planets, setting the stage for a cosmic ballet billions of years in the making. At the heart of this swirling cloud, a star is about to be born. The immense pressure and heat at the center of the nebula ignite nuclear fusion, the engine that powers stars. Our own sun, a rather ordinary star in the grand scheme of things, was born from such a process, igniting some 4.6 billion years ago. As the young star ignites, it bathes the surrounding disk of gas and dust in light and heat. This disk, known as a protoplanetary disk, is where the magic of planet formation truly begins. Imagine a giant cosmic frisbee, a swirling disk of material orbiting the newborn star. This disk is far from uniform. It's a chaotic mix of gas, dust, and ice, all swirling around the central star. Within this swirling chaos, tiny particles begin to collide. Dust grains no bigger than the width of a human hair bump into each other. These collisions, though seemingly insignificant, mark the first step in a process that will eventually lead to the formation of planets. Over millions of years, these tiny particles begin to stick together, forming larger and larger clumps. This process, known as accretion, is the engine that drives the formation of planets. As these clumps grow larger, their gravitational pull increases. They attract more and more particles, growing larger and larger. Imagine a snowball rolling down a hill, gathering more and more snow as it goes. This is similar to what happens during the accretion process. These growing clumps, now kilometers across, are called planetesimals. They are the building blocks of planets, the seeds from which entire worlds will grow. Within the protoplanetary disk, these planetesimals are on the move. They collide with each other, sometimes sticking together to form larger objects and sometimes shattering into smaller pieces. It's a chaotic and violent time, a cosmic demolition derby with planets as the ultimate prize. Over millions of years, the largest planetesimals emerge victorious, having swept up most of the material in their orbital path. These planetary embryos, as they are known, are well on their way to becoming full-fledged planets. Section 4. Layered worlds. Planetary differentiation. As these planetary embryos continue to grow, their interiors begin to heat up. This heat comes from a variety of sources: the decay of radioactive elements, the heat of accretion itself, and the gravitational pressure of the planet's own mass. This internal heating leads to a crucial process called differentiation. Imagine a jar filled with oil and water. When shaken, the two liquids mix together, but let it sit for a while, and the denser water will settle to the bottom while the lighter oil will rise to the top. A similar process occurs within planets. As the interior heats up, denser materials like iron and nickel sink towards the center, forming a metallic core. Lighter materials, such as silicates, rise to the surface, forming a rocky mantle and crust. This process of differentiation is what gives planets their layered structure. Section 5. Our cosmic neighborhood, the solar system. Today, our own solar system is a testament to the power of these planet-forming processes. 4 rocky planets, Mercury, Venus, Earth, and Mars, orbit relatively close to the Sun. These terrestrial planets, as they are known, are thought to have formed in the hotter inner region of the protoplanetary disk, where only rocky materials could condense. Further out, we find the gas giants, Jupiter and Saturn, and the ice giants, Uranus and Neptune. These massive planets, with their thick atmospheres and systems of rings and moons, formed in the colder outer regions of the disk, where they could accrete not only rock and metal, but also vast amounts of gas and ice. The asteroid belt, a region between Mars and Jupiter, is thought to be a remnant of the early solar system, a collection of planetesimals that never quite managed to coalesce into a planet. Comets, icy wanderers from the outer reaches of the solar system, provide us with clues about the conditions that prevailed during the early stages of planet formation. By studying our own solar system and the many other planetary systems that have been discovered in recent years, we are gaining a deeper understanding of the processes that gave rise to our cosmic neighborhood.